We have previously seen examples for search and substitute commands. Let us see a few examples for flags that you can use with the substitute command. The G flag will help you replace all occurrences within a matching line. By default, only the first matching portion will be replaced. Let's see an example. Suppose I want to search for apple and replace it with custard. So I can use percentage as my range. So search will happen for all the input lines. My search string is apple and replacement is custard. Let's see what happens by default. So there are 4 matches, but by default only the first match in each matching line will be replaced. So you can see second and third matches were not replaced. Let me undo this. And now if I add the G flag, then every match in all the matching lines should be replaced. And you can see that is what we get. Let's undo and go back. If you add the C flag, then you will be asked for confirmation before each replacement. Let's see an example. So this was our previous substitute command. Now I'm going to add C. So before each replacement, I should be asked for a confirmation. So let's see how that looks. I'm going to press enter. So this is the current highlighted match and you are asked what to do with it. You can use Y to confirm yes, N for no, and so on. So I'm going to press Y. So that was replaced. And then the next match is highlighted. This one I'm going to say no. For this I'm going to say yes. And for this I'm going to say no. So let's undo and go back. If you use the lowercase I option, then it will ignore case for the search term. So this time, let me search for cat. So currently, ignore case option is set. So let me first unset that option. And now if I try to search for cat, only the exact case match will be highlighted. So let us try to replace all occurrences of cat with dog. So by default, the match will happen case sensitively, provided the ignore case setting is off. So I'm going to press enter and you can see only the exact match for lowercase cat was replaced. Let me undo that. And if I use the I option, it should replace irrespective of case. So I'm going to press enter. So you can see all the matches of cat irrespective of case were replaced. Let's undo that. And now let me set ignore case and let us repeat our previous substitute commands. So this time I'm going to not use the I option. So because ignore case is on, all these 4 matches will be replaced. Let's undo that. And now if I use uppercase I, then this will become case sensitive. So only this match should be replaced. Let's press enter. Let's undo and go back. So as mentioned earlier, these flags are applicable only for the substitute command. There are other ways to ignore case, like setting the ignore case option, and few other options for search commands. So that will be covered later. And as we already saw with these examples, flags can be combined. For a complete list of flags and more details, you can go through the help topic s_flags. Let us see how to use line and word anchors. By default, regular expressions will match anywhere in the text. You can use line and word anchors to specify additional restrictions regarding the position of matches. These restrictions are made possible by assigning special meaning to certain characters and escape sequences. The characters with special meaning are known as metacharacters. In case you want to match these special characters literally, then you can escape them with a backslash character. Caret and dollar are metacharacters to match at start of line and end of line respectively. Let us see an example. Suppose I want to search this. So there are two matches here. But suppose I want to match only at the start of the line. So in such cases, I can add the caret metacharacter. So now I should get only one match because this particular occurrence is not at the start of the line. Let's see an example with end of the line. So I'm going to match closing parenthesis and I'm going to use $anchor and press enter. So you can see these three are the only matches. This particular character is not matched because there are more characters after that. If you combine caret and $metacharacters, you can match empty lines. So let's see an example. Caret followed by $. To press enter. So there are two matches in this particular sample file. You might wonder why this particular line is not matched. So because there are some empty spaces in that line. So let me show that. So there are space characters, which is why this did not match. Empty line rejects. Let's go back. Next, let us see how to match start and end of a word. Word characters include alphabets, digits, and underscore. So if you use backslash followed by less than key, then that particular pattern will be matched only if that is at the start of a word. If you use backslash followed by greater than key, then that particular pattern will be matched only if it is at the end of a word. You can use both start and end if it is needed. Let's see some examples. Suppose I search for his. You can see there are a lot of matches, but I don't want to match his if there are word characters before that. So what I can do, can add backslash followed by less than key. So now these particular matches won't occur because there are word characters before his. Remember that underscore is also a word character. Now if I use his followed by backslash and greater than key, then you will get matches only if his is at the end of a word. So history does not match because there are characters after S, and here also there are characters, and recall that numbers are also part of word characters. So this is also not a valid match. And now let us combine both start and end of word. So these are the only two matches Hyphen is not a word character, so this is a whole word. Let's go back. End of line definition might vary depending on your system and file format setting. So these could be carriage return, new line, or a combination of these two characters. You can go through the help topic pattern hyphen atoms for more details. Let us learn about the dot meta character. If you need to match any single character other than the end of line characters, then you can just use the dot meta character. If you need to include end of line as well, then you need to use backslash underscore followed by dot. Let us see a few examples. If I use C dot T, then it will match C followed by any single character and then a T. As mentioned earlier, this will not match a end of line character. So this is not matched. You can use C backslash underscore dot and T if you need to match across lines as well. Let me give another example. C dot dot T. This will match C followed by any two characters and then a T. You will later see how backslash followed by underscore is used in many more places to include end of line while specifying a search pattern. Let us learn about greedy quantifiers. Quantifiers can be applied to literal characters, dot meta character, groups, backreferences, and character classes. First, let us see about the star greedy quantifier. So this will match 0 or more times. Let's see an example. If I use AB followed by C the star, then this will match A followed by B followed by 0 or more occurrences of C. So you can see AB is a match, ABC is a match, ABCCC is a match, and so on. Since this is a greedy quantifier, all possible occurrences of C will be matched. Next, let us see how to match one or more times. So in this case, you have to use backslash followed by plus. So let's modify our previous search. Instead of star, I am using backslash plus. So now C has to match at least one time. If I change plus to a question mark, then C will be matched 0 or one time only. So you can see, even though there are more occurrences of C, only the first occurrence is matched. If you are searching in the backward direction, then we cannot use backslash question mark. Instead, you can use equal to. Let's go back. Next, let us see how to use range of numbers. So backslash and within curly braces, if you use a start and end range, then this will match from M to N with both lower and upper as inclusive. Let's see an example. Suppose I want to match C between 1 and 4 times. So I can use backslash curly brace 1, 4. The ending curly brace can be either used directly or with a escaped version. So these are the 3 matches in this particular test file. So minimum 1 and maximum 4. If you leave out the upper range, then this will match at least m times. If you leave out the starting range, then it will match maximum up to n times, 0 times included. If you specify just a single number, then exactly that many number of times will be matched. So let us see examples for these three cases. Let us modify the previous example by removing the upper range. So now you can see C is matched 1 or more times. So this is same as using plus. Let's modify this example again and we'll use it as 2 comma. So at least 2C has to be matched. And now let us use comma 4. So starting range is not specified, which means C can match 0 times as well. Maximum is 4 times. So here C is 0 times and here C is 4 times at max. If you use comma 1, then this will be same as using backslash question mark. Next, let us specify the exact number. So let's say 3. So C will be matched only 3 times, no less and no more. Let's go back. Greedy quantifiers will consume as much as possible, provided the overall pattern is also matched. So let's see an example. Suppose I want to match error followed by any number of characters and then the string valid. So this particular line is a match because it contains error followed by any number of characters and then followed by valid. Now let me show a previous example. A, B, C followed by star. So in this case, C is matched as much as possible. So it consumes all of these characters. But when we specify error dot star followed by valid, why is this dot star not consuming rest of the line? In fact, if I remove valid, you can see from error it matches till end of the line. So what is this special case? Error dot star and then valid. So as mentioned here, greedy quantifiers will consume as much as possible, provided the overall pattern is also matched. So in this case, the regular expression engine will in fact match till end of the line. But if that happens, then valid cannot be matched. So the engine will try to give up characters for dot star. So dot star means for match any character except end of lines 0 or more times. So it will try to give up characters until a match is found. So in this particular line, there is valid after error. So there is a match. In this case, there is no valid after error. So this particular line does not match. How the engine handles varying amount of characters depends on the implementation. So there are variations like backtracking, NFA, and so on. For more details, you can go through the help topic pattern-overview. If you are familiar with other regular expression flavors like Perl, Python, and so on, you might be surprised by use of backslash in these cases. So later we will see how to use backslash v modifier. So this will enable very magic mode, and in this mode, the backslash for these quantifiers will not be required. Non-greedy quantifiers match as minimally as possible, provided the overall pattern is also matched. First, let us see how to match 0 or more times as minimally as possible. Suppose you wanted to match from T till the next occurrence of A. If you use greedy quantifiers, you can see it matches from first T till the last A in the line. Instead, if I use non-greedy quantifier, then this will match from first T to the very next A. And if there are multiple matches, then they will also be matched. So the syntax is backslash and within curly braces use a hyphen or a minus character. So let me show this with a substitution command as well. If I use greedy quantifier, then from here till here will be replaced with X. Let's undo. And instead, if we apply non-greedy quantifier, then there will be two matches. Let's undo. In general, we can use backslash and within curly braces, we can give a range between m to n, and both these numbers are inclusive. The only difference is you have to use a minus or a hyphen character at the start. If this is not present, it becomes a greedy quantifier, and you can leave out either m or n as we saw with greedy quantifiers. So let's see an example. Suppose if I say A, B followed by a range m comma n, so let's say 2 comma 5. So in case of greedy quantifiers, B will be matched as many times as possible. If we use minus 2, then this will become a non-greedy quantifier. So match as minimally as possible. So in this particular case, it will always match only a maximum of 2 B's. So you can see only 2 occurrences of B are matched. The overall pattern also has to be satisfied. So if I add an additional C, then it will try to match between 2 to 5 as long as C is also found. So this will behave exactly same as the greedy quantifier. For more details, you can go through the help topic pattern-overview. The dot meta character can be used to match any character. To create a custom placeholder for a limited set of characters, you can use character classes. These have their own version of meta characters, and there are special predefined sets for common use cases. To match a set of characters, you should place them within square brackets. So this will be matched only once. If you add a caret character at the start, then it will invert the set. So in this example, this will match other than lowercase vowel characters. By using a hyphen between two characters, you can create a range. So A hyphen D will match A or B or C or D. Next, let us see a few of the predefined character sets. You will note that these have lowercase version and uppercase version. So backslash and lowercase a matches any alphabet character. Backslash and uppercase a will match other than alphabets. So backslash and lowercase a is equivalent to a hyphen z and uppercase a hyphen uppercase z. backslash and uppercase A adds a character to the start. Similarly, there are lots of such predefined sets. Lowercase l matches lowercase alphabets. Lowercase u matches uppercase alphabets. Lowercase d matches any digit character, so that is 0 to 9. Lowercase o matches any octal character, which is 0 to 7. Lowercase x matches any hexadecimal character. So these are 0 to 9 and A to F. Lowercase h matches alphabets and underscore. Lowercase w matches any word character. So in addition to alphabets and underscore, this also matches digits. You might recall this definition from word boundaries. Lowercase s matches space and tab characters. To add end of line character, you can use a backslash underscore instead of backslash. So for example, if you use backslash and lowercase s, it matches only space and tab characters. If you use backslash underscore and then s, it will help you match across lines as well. So let me give a simple example here. So dot, and then I want to match end of line character and then a uppercase alphabet. So I can use backslash underscore s and followed by backslash u. So this can match across lines and it matches any space or tab character as well. Let us see a few examples for character classes. So if I want to match cut or cut, I can use C and within square brackets O or U followed by T. So this matches cut or cut. Next, let us place two character classes next to each other and let's also add word boundaries. So this will create four combinations OO, ON, TO and TN. Let's see an example with line anchors. Let us match O or N two or more times. So this will match no, non, noon and on. Next, let us invert a character class. So suppose I want to replace all text surrounded by double quotes. Then I can use double quote, caret key, and the set of characters I want to invert. You can use the plus quantifier to match one or more times and then followed by a double quote character. Let's say I want to replace this with X. Next, let us see an example with character set. So let's say I want to replace all consecutive sequence of digits with a dash. So backslash D will match any digit character and plus quantifier helps to match one or more times. Let's replace with hyphen. Next, let us see how to match numbers greater than 100 with the optional 0 prefix. So 0 star and 1 to 9 slash D, which will be 2 or more times. So we are using 0 star to match any 0 prefix. After that, we need at least one match of numbers starting with 1 to 9. After that, we need at least two more digits. So this will match numbers greater than 100 with the optional 0 prefix. If you use just \d and 3 comma, then this 0 star may match 0 times, so that \d matches 3 times. So remember that star is a greedy quantifier, but it still tries to find a match that satisfies the overall expression. So thus, we need to separate out the first digit and the following 2 or more digits. Next, let us see how we can replace all non-word characters. So semicolon, hyphen, backslash, these are all non-word characters. Let's replace them with a space. Now let's go back. The predefined character sets do not have a special meaning to use within square brackets. So something like \d\s within square brackets will only match \d or s. So let's see an example. \d\s. So you can see it is matching d and s. And if I add a backslash character, then that will also be matched. Instead, if we want to match any digit or space character, then you have to specify them manually, or you can use named character sets, colon, digit, and colon, space. If you want to know a list of such named sets, then go through the help topic. So alnum is first such named set. So this will allow us to look at all the sets that follow. So there is alnum, alpha, blank, control characters, and so on. Let's quit this. The predefined sets like \d, \s, and so on are also better in terms of performance compared to equivalent bracketed versions. For more such details, you can go through the help topic, character-classes. Let us see a few examples for alternation and grouping. Alternation helps you to match multiple terms, and each of these terms can have their own independent anchors. We can use backslash and the pipe character combination to separate the different search patterns. So let's see an example. Suppose I want to match min or max. So I can provide these two search patterns separated by backslash and a pipe character. You can use one or more alternatives. So for example, 1 or 2 or 3 or and or read, and so on. Next, let us see an example with anchors applied to the search patterns. So for example, I want to match par as a whole word only, and I want to match lines ending with D. So I'll add the $key. So you can see this matches par only as a whole word, and it matches D only at the end of the lines. Let's go back. Often, there are some common things among these alternatives. In such cases, we can group them using a pair of parenthesis metacharacters. So in mathematics, you might have seen such an expression. ABD plus ACD can be rewritten by taking out AD, which are common among these two terms outside, and within parenthesis, you can say B and plus C. Similarly, if we want to match ABD or ACD, we can take out A and D outside and within parenthesis, you can say B or C. Apart from taking out common terms, grouping a pattern allows you to apply quantifiers, and we'll see few more use cases like backreferences later. So let's see some examples. Suppose I want to match hand or handy or handful. So you can either spell them out separately, or we can make use of the fact that hand is common among these three search patterns. You might wonder why the entire word is not highlighted. So that's because of precedence. So I'll explain that later. If I change this to handful followed by handy and followed by hand, you will see the entire match is highlighted. So now between these three terms, hand is common. So what we can do is we can specify hand, and within parentheses we can specify the unique terms. So we need to match Y or full or nothing. So to do that, we can make this group optional. Let me show another example with quantifiers. So I want to search for 2 any number of times. So this will match TO or TO 2 times, 3 times, and so on. So this example might be better realized by using the substitute command. If I replace all occurrences of 2 with X, then this will be changed to X, this will be XX, this will be XXX, and so on. Instead, if I apply the quantifier, then each of these will be a separate match. So there will be only 4 replacements. You can see there are only 4 X. Let's see one more example with grouping. Suppose I want to match read or released or received. So RE and ED are common. RE and ED are common, and within parentheses we can specify the rest of the terms. To match read as well, we can make this optional. So let's go back. When you use alternation, you have to be aware of the precedence. Suppose you want to match R or spare. Which one should get precedence? You can see R is within this bigger word as well. So the first rule you need to remember is the alternative which matches earliest in the input gets precedence irrespective of the order of these alternatives. For example, let's consider this line, and I want to replace R or spared. So whichever term matches earliest in the input will get preference. So in this case, the order will not matter, because when it sees R, so there is no conflict between these two terms. And when it sees spared, this will always match before ARE can be matched, because this S occurs earlier than A in this line. So if I use R followed by spared, I'll get this result. And let me undo that and change the order. and this time I'll get the same result. Next, let us see where order can matter. So this will happen if the alternatives have same characters at the start. So between spa and spad, the first three characters are same. So in this case, the order in which you specify these two alternatives will matter. So the leftmost alternative gets precedence. So for example, in this line, if I substitute spa or spad, SPA will get preference. So this particular term will never match because SPA is part of this larger word and this is specified earlier in this alternation order. And let me repeat that by changing to spad followed by spa. So in this case, this term gets precedence. So spad will be replaced with X. If not, SPA will be replaced with X. So you can see these two lines were having the same content, but while replacing, the order was different, so we got different results. So let me summarize this again. The alternative which matches earliest in the input gets the precedence. But if the alternatives match from the same location, then the leftmost alternative gets the precedence. Let us look at back references. The groupings we saw earlier are also known as capture groups. The text captured by such groups can be referred later using back references. And these back references can be used both in search and replacement sections. So this is the grouping syntax which we have seen earlier. If we add a percentage prefix to the opening parenthesis, then it becomes a non-capturing group. We'll see examples for both of these. To refer to these capture groups, we can use 1 to 9. The leftmost opening parenthesis is given the number 1. Second leftmost opening parenthesis will get the number 2 and so on. To refer to the entire matched portion, you can use \0 or ampersand. Let us look at some examples. If you recall, \A is a shortcut to alphabet characters. So if we put this inside a capture group and then immediately follow by \, and 1, this will help us to match consecutive repeated alphabets. So let's type that / and lowercase a refers to alphabet characters. And now let's capture the text that is matched by \A. To refer to the exact character matched, so \A can match 52 different characters, but we want the exact character that is matched because we are looking for consecutive repeated alphabets. So we can refer to this particular character that was captured by using \1. So you can see a few matches here. Lowercase e 2 times, uppercase T 2 times, and so on. The case also has to match. You can apply quantifiers to these back references as well. So suppose we want to replace all such consecutive repeated alphabets, then we can use, so within capture group we have \A, and when we specify the back reference we can also add the quantifier plus. So this particular back reference has to match one or more times. Let's say we replace it with 1, 2, 3. So these three matches should be replaced with 1, 2, 3. Next, let's see an example with referring to the entire matched portion. So in this case, we don't have to specify a capture group. So suppose we want to surround numbers with parentheses. So to match one or more digits, you can use \d and the plus quantifier. And now we can replace it with opening and closing parentheses, and in between the entire matched portion, which may or may not have other capture groups. So whatever text is matched in this search pattern can be referred by using the ampersand key, or you can use \0. You can see numbers have been surrounded by parentheses. Next, let us see how to swap words that are separated by a comma. So to match word characters, we can use \w. So word characters are alphabets, numbers, and the underscore character. We want to match this one or more times, and there are two words that are separated by a comma. So this helps us to match words separated by a comma. We want to swap them. So we need to capture these two words separately. So surround them by a parenthesis and another capture group here, and in replacement. So this is the leftmost opening parenthesis. So this is capture group 1 and this is capture group 2. We want to swap them, so we'll say \2, \1, and such words can occur more than once in the line. We'll use G flag. Let's see the result. So you can see words have been swapped. Let's undo. Next, suppose I have a input string like this. There are certain sequence of characters that are surrounded by a single underscore, and sometimes there are double underscores. I want to replace two underscores with a single underscore, and if there are only one underscore consecutively, then I just need to delete them. So I can optionally match an underscore character and then match one more underscore character. So this will effectively match underscore once or twice. If it is twice, then this capture group will have a single underscore. If it is matching only once, then this will be empty. Even though question mark is a greedy quantifier, because overall pattern has to be satisfied, this will become empty. So we can refer to that position in the replacement string. So double underscores will become a single underscore, and if there is only one underscore, this will be empty, so that gets deleted. Let's do that. Next, let us see an example with non-capturing group as well. So suppose I have numbers that are separated by one or more occurrences of ABC. So this particular ABC sequence is repeated one or more times. So I want to match such a sequence, that is numbers separated by one or more sequences of ABC. And in the result, I want to put this second number first, use a colon character, and then put the first number next. So let us see how we can use capture groups as well as non-capturing group. So we know we have to match two sequences of digits. And since they are going to be swapped, we can capture them separately. In between these two digits, we have one or more ABCs. So since ABC is more than one character, we need to apply a grouping to be able to specify a quantifier. This particular text is not needed in the output. So we can prefix a percentage to the opening parenthesis so that this portion is not captured. So now this is capture group 1, this is non-capturing group, and this is capturing group number 2. So in the output we can say \2 colon \1, and that's it. So this particular text should get changed to 24 colon 12. Let's undo it. Instead, if you had used a capture group for this portion as well, then this becomes capture group 1, this is capture group 2, and this is capture group 3. So the replacement section will require \3 colon and \1. So which one to use depends on your preference, but the general rule of thumb is if a particular portion is not needed in the replacement section, you can use a non-capturing group. Next, let us see what happens to a capture group on which a quantifier is applied. When you back reference that particular group in the replacement section, you will not get the entire match that is matched by this group and the quantifier. So let me explain that with an example. Suppose I have a string like A space and then some digit characters. I want to match 3 digits at a time, one or more times, and then my aim is to surround such sequence of digits with a parenthesis. But first we'll see what happens if we just naively try to use just a single capture group. So my text has A followed by digits, but I want to match only in groups of 3. So instead of plus quantifier, I can use exactly 3 times. And this grouping of 3 digits can occur one or more times. So I need a group so that I can apply a quantifier on that. So now I want to replace A with B, and whatever digits are matched here, I want to surround them within parentheses. So inside this I need to refer the text that is matched, right? So usually you will just use \1, but this will not give the result which I need. So this particular text, I want to change it to this output. But if I use this regular expression, I'll get this output. So why is that? Because this particular quantifier is outside the group. So first time these 3 digits are matched. This is a greedy quantifier. So what will happen? It will also match this particular sequence and then this sequence as well. But in the regex search pattern, we have only one capture group. So first time it has 1, 2, 3. Next time it has 4, 5, 6. And the third time it has 7, 8, 9. So once all this is done, when you use \1, you will just get 789. So what is the solution? We need to use a capture group on this group as well as this quantifier. So now let's get the previous substitute command and let's apply a grouping to cover both this inner group and the quantifier. So now this becomes the capture group 1 and this becomes capture group 2. So this should work. You can see that entire digit portion has been surrounded by a parenthesis. And if we apply on it on this particular line, then you will see that this sequence of 3 digits has been repeated twice and then parenthesis is applied on this portion. Any other remaining digits will be left as it is. Let's undo that. So in this type of scenario, this inner group is needed only to apply this quantifier. We don't need the text later, so we can use a non-capturing group. We'll get the same result. So to summarize, referring to text matched by a capture group with a quantifier will give only the last match, not the entire match. We need to provide another capture group around such a group and the quantifier together to get the entire matching portion. If the inner group is not needed, then it's an ideal candidate to use non-capturing group. You can use lookarounds to create custom anchors and add conditions within the search pattern. These assertions are also known as zero-width patterns because they add restrictions and are not part of matched portions. Vim syntax is different than what is usually found in other programming languages. The pattern used in the assertion is always specified before the sequence of backslash and the @ key. So for example, in other programming languages, this is the type of syntax that is used. In Vim, the pattern to be asserted is specified first and the look ahead syntax is specified next. So this is another example. This is the pattern to be asserted. So that is specified first and then rest of the syntax comes later. So there are 4 types of lookarounds: negative look ahead, positive look ahead, negative look behind, and positive look behind. Let us see a few examples for each of these assertions. So suppose you want to match eyes only if is not followed by a digit character. So this is our pattern to be matched and this is the assertion. So a digit character. We don't want this pattern to be matched. So we are using negative look ahead assertion. So the syntax is \@. So this part comes for all types of lookarounds. And when we use exclamation, then this becomes negative look ahead assertion. So let us use this as a search pattern. So you can see it matches eyes as long as there is no digit character immediately. So here there's a \# character, this is backtick, this is alphabet D, this is T, this is a dot character. So all of these are valid matches. But these are not matched because after eyes there is a digit character. Same for this example. So this is the same search pattern used in a substitute command. Substitute i's only if it is not followed by a digit character. So let's say it is replaced with x and all the occurrences are replaced. So you can see this will be replaced with x, this also will be replaced with x, but not this because there is a digit character. Let's undo that. Here's another example. So this will match par as long as whole word par is not found later in the line. So this particular sequence is not matched because there is a whole word par later in the line. Now this itself will be a valid match because after this there is no whole word par. So on this particular line, if we apply this substitute command, this will not be replaced. This will be replaced with x and this also will be replaced with x. So recall that lookarounds do not consume characters. They are only used for asserting a particular condition. So the way this works is the engine finds the normal search pattern terms and after this match is found, it checks whether this particular assertion holds true or false. So when this is matched, it will check whether there's whole word par after this point. So in this case, it is there, but we don't want, so our assertion is this should not match. So this will fail. When it comes to this, the assertion will hold true because after this match, there is no whole word par. Same for this particular match as well. Next, let us see an interesting application of negative look ahead. So we can negate a particular group. Suppose I want to match at followed by par. So at followed by par. So these two lines are a valid match because there is at and then there is par after 0 or more characters. Same for this particular line as well. Now I want to add a condition that in between at and par, I don't want GO. So between these two matches, the characters present should not have GO. So this is a valid match, but this will fail because there is GO. So how to specify this? So this was our earlier search term. So what we need to do is negate a particular group. So the sequence I don't want to match is go. So to do that, you can use negative look ahead. So once this condition is satisfied, we can match a character using the dot metacharacter, and that we need to repeat 0 or more times. So we can put this whole thing inside another parenthesis. So now only this line is a match and this will fail because it found GO in between at and par. Next, let us look at negative look behind. So we need to add this less than key before the exclamation mark. So exclamation indicates negative assertion. When we use it by itself, it becomes look ahead. When we prefix less than key, it becomes look behind. So for example, this is the term we need to match as long as the underscore character is not the previous character. So to do so, we'll specify underscore and then backslash at less than exclamation. So this will match eyes as long as underscore is not the previous character. So even start of the line will be a valid match. So suppose I add something like iced tea here. And now let me search for this particular term. Underscore is the character I don't want to match. And the actual string to match is ice. So these are all valid matches. This will not match because there's an underscore character before I. And start of the line is also a valid match because before I, the underscore character is not present. So here's another example. I want to match dog as long as cat is not present earlier in the line. So cat can be at anywhere before dog, right? So we need dot star, and this is what I don't want to match. So I will say backslash at less than exclamation. So match dog as long as cat is not present earlier in the line. So now this should be easier to understand. So we have seen negative look ahead and negative look behind. So in case of positive, those particular characters should match. So for example, match eyes only if there's a digit character present immediately after eyes and digit character. So you might ask, why don't we just use eyes and backslash d? So the difference is the pattern which is part of the look around is not part of the match. So you can see only eyes is highlighted. The digit character is not highlighted. So this will become more clear when we use the substitute command. So in this line, we want to replace eyes only if it is followed by a digit character. So when you do the search, you can see only this particular string is matched. And now if I specify eyes slash d and then if I use x, this whole term will be replaced. But I don't want to replace this digit character. So in that case, I'll apply a positive look ahead. So you can see only ice is replaced, the digit character is left as it is. Similarly, for positive look behind assertion, you have to prefix a less than key. So look ahead assertion used equal to, and if we prefix a less than key, it becomes look behind. So this will match eyes only if there is a underscore character before underscore and eyes. So these are not valid matches because the character before I is not an underscore character, and these two are valid matches. When you are using look behind, you can also specify the number of bytes to search for. So this is helpful to speed up the matching process. Earlier we saw an example, match dog as long as cat is not present earlier in the line. So the thing is, the lines could be very long. So the search engine has to go through each and every character that is present before that particular match. So this can take a long time. In such cases, we can limit how many characters are searched for the assertion. So for example, let's say I want to search only the previous 11 byte characters. So in such cases, between this at and less than key, I can say 11. So let us see an example. So match dog only if cat is not found in the previous 10 characters. So in this line, there is a match for cat, but the previous 10 bytes do not have cat. So this is a valid match. In this line, there is dog, but the previous 10 bytes also has cat. So this is not a valid match. So in this way, you can speed up look behind patterns if you specify number of bytes to match between the at and less than key. As we have seen earlier, both greedy and non-greedy quantifiers will try to satisfy the overall pattern by varying the amount of characters that are matched by these quantifiers. If that is not desirable, you can use atomic grouping. So when this is applied to a specific subpattern, it will not give back characters that it has already matched. Syntax wise, this is similar to lookarounds. So suppose this is the pattern you want to protect. You need to add backslash, at, and greater than key as a suffix to this pattern. Let us see an example where a naive solution using greedy quantifiers will cause an issue. Our goal is to replace numbers greater than or equal to 100 irrespective of any number of leading zeros. So suppose this is the input and we want to surround numbers greater than or equal to 100 with parentheses. So this is a naive solution using greedy quantifiers and that causes some issues. So let us see why. 0 star matches leading zeros and we need to match a digit character 3 or more times. So this will help to match numbers greater than or equal to 100. Replacement is surrounding the matched portion with parentheses, but this solution will not work for all numbers. So as you can see, even 035 is surrounded by parentheses. Why? If you go back to the substitution command, 0 star is a greedy quantifier, but it will give up the zeros it has matched in order to match the overall pattern. So that's why this failed. So let us undo that. If we wanted to stick with greedy quantifiers, we can change this pattern a little bit. So instead of matching a digit character at the start, we can change it to 1 to 9. So now 0 star and 1 to 9 cannot conflict. Whatever this has matched will play no role when it comes to matching 1 to 9. So one digit is taken care here. So we need to reduce this to 2. So now you can see only these two numbers are surrounded by parentheses. Instead of all this, we can also use atomic grouping. So let's go back to the first solution. So this is where we faced an issue because 0 star gave up the characters it has matched for this pattern. So now we need to protect this sub pattern from giving back the digits it has matched. So we'll make this a atomic grouping. So to do so, we need to add backslash at and greater than key. So this entire thing is our atomic grouping. Whatever is matched inside this will not be influenced by what comes later. So you can see only these two numbers are matched. In case of 035, this sub pattern matches the first 0 and it will not give back that character. So backslash d cannot match 3 digits because 0 is taken care by this atomic grouping. So now we get the solution that is desired. Some of the positive look behind and look ahead use cases that don't need to be zero with assertion can be replaced with \zs and \ze respectively. These will help you to set start and end of the match. So let's see a couple of examples. The portion that matches before \zs won't be part of the match. So this will feel very familiar to positive look behind. The difference is this only sets the location of the match. This is not a zero with assertion. So suppose this is your input line and you want to retain only the first character of each word. Rest of the characters you want to remove. So you can match the start of a word using word anchor, and this particular character you can exclude from the match by setting the start of the match. So portion that comes after this will be part of the matched portion, whereas this particular character will not be part of the match. So we have captured the first character of a word. So remaining characters we need to delete. So that will be some 0 or more word characters, as well as there could be non-word characters between words. So we can use uppercase W to remove that. We don't need anything in the replacement section because we want to delete these characters. And if we apply the G flag, all such occurrences will be replaced. So you can see the first character of the word is not part of the match. After that, we have 0 or more word characters and 0 or more non-word characters. So if we execute this substitute command, we'll get this secret. So let's undo that. So the same thing you can also implement using lookarounds or using captcha groups. So when you use lookaround, this initial word character will be positive look behind assertion. So these characters will be removed. In the captcha group case, we have the starting word character in this first captcha group, and remaining characters will be removed because in the replacement we are only back referencing the character that was captured. So in this way, you can either use captcha groups or lookarounds, or you can also use \zs to set the start of the match. So among these three, I prefer this because this is much easier to write. Next, let us see a similar example with setting the end of the match. So now the portion that comes after \ze won't be part of the match. So suppose you want to match eyes only if it is followed by a digit character. So eyes followed by a digit character. Only such matches are needed, and in such cases we need to replace only the eyes part with X. The digit part should not be replaced. So in such cases we can match eyes and then we can set the end of the match. So only these characters will be part of the match, and whatever comes after ZE will not be part of the match. But those characters have to be matched for this search pattern to succeed. So we need a digit character. In the replacement, we are replacing this match with X. Let's undo that. The same thing, you can use positive look ahead. So this particular digit character is part of the positive look ahead assertion, or you can capture the digit and put it in the replacement section. Again, if you see among these three options, this is much easier to write. Also, as per the help topics, you can use these multiple times. Only the last one encountered in a matching branch will be used. Let us learn about magic modifiers. These escape sequences change certain aspects of the syntax and behavior of the search pattern that comes after such a modifier. You can also use multiple such modifiers as needed for particular sections of the pattern. First, let us see about magic and no magic modes. The magic mode is the default setting. But if you are in some other mode, then you can use backslash and lowercase m to specify a pattern with magic mode. We'll see an example later. By using backslash and uppercase m, you will get no magic mode. The only difference between this mode and magic mode is that dot, star, and tilde are no longer metacharacters, but you can still get that behavior by escaping them. The line anchors behave the same as magic mode. So here's a simple example. By default, we are in magic mode. So A dot B will match A followed by any character other than new line or end of line characters, and then followed by B. So these are all valid matches. A equal to B, A less than B, ACB, or even A dot B. So this is in magic mode. You can also explicitly specify magic mode by using backslash and lowercase m. And now if I change it to uppercase m, this becomes no magic mode. In this mode, dot is no longer meta character. So this will match A dot B only literally. But if you still want a dot meta character, then you can escape that using backslash. So this will behave same as A dot B in magic mode. Next, let us see about very magic mode. So this is helpful if you are coming from other programming languages such as Perl, Python, or JavaScript. So by using backslash and lowercase v, you can use parentheses, curly braces, plus, question mark, etc. as meta characters without having to prefix them with a backslash character. So from the help topic magic, use of backslash v means that after it all ASCII characters except 0 to 9, A to Z alphabets and underscore have special meaning. So in other words, except the word characters, any character like parentheses, curly braces, etc. will behave as meta character without a backslash prefix. So let's see some examples. Suppose you want to match his as a whole word. So in the default mode, that is the magic mode, you have to use backslash less than for start of the word anchor, then our word to search, and end with backslash and greater than key. So you can see it matches his only as a whole word. If you use very magic mode, then you don't need this backslash characters. So just the left and right, less than and greater than keys will act as start and end word anchors. In such cases, when the very magic mode is on, you need to match a less than key, then you need to escape it. These modifiers don't have to be specified at the start of the regex pattern. So suppose you need to match A less than B literally, followed by the word end as a whole word, then you can use A less than B. So by default, magic mode is on. So this will match A less than B literally. And then we need to match 0 or more characters, followed by end as a whole word. So in magic mode, you will use backslash version of the word anchors. Instead, you can activate very magic mode so that the backslash characters are not needed. Here's one more example. Suppose you want to match 1 or 2 or 3. So in magic mode, you have to escape the pipe character. Instead, if you use very magic mode, we can specify pipe directly as the meta character. So same case for plus or question mark or curly braces and so on. Here's a great example where using very magic mode helps you to shorten the regex pattern very much, and it is more readable as well. So for example, if you wanted to swap comma separated whole words, then in magic mode you will use a lot of backslashes. Instead, in very magic mode, you just have to specify backslash v once, and then you can just normally specify parenthesis and the plus quantifier without having to escape them. So this becomes a shorter regex pattern, and it is more readable, as well as it helps if you are using regex in other programming languages such as Perl or Python. Finally, let us see very no magic mode. So earlier we saw no magic mode, but in that the line anchors were still specified by using caret and dollar as meta characters. In very no magic mode, even those will become ordinary. So you will have to use backslash and caret or backslash and dollar if you need line anchors. So here's what the documentation says. Use of backslash uppercase V means that after it only backslash and the delimiter character, so that is usually a slash or the question mark, will have special meaning. So for example, if you want to match these characters literally, then using very no magic mode will be easier. So by default in magic mode, in magic mode, these 4 characters will be special. So you need to escape them. If you use no magic mode, then you still have to escape the caret and dollar keys. So let me show that. In no magic mode, you still have to escape the line anchors to match them literally. Instead, we use very no magic mode, then all of these characters are ordinary, nothing special about them. And now, if you want to mix and match with other modes, so for example, after matching this, let's say I want to match ABCD later. So usually you will say dot star and ABCD, but in very no magic mode, these are not special. So we need to either escape them, so you can see these matches, or you can change to another mode. So you change to magic mode, then dot and star are special again. Similarly, if you want to match this particular line, so let's say we have these two lines, and normally we'll match th at the start of the line by using caret and th. If very no magic mode is active, then you will have to escape the caret key. Similarly, for end of the line anchor, you will have to use $. You can control case sensitivity by using backslash and lowercase c or uppercase c. These escape sequences will override flags and settings. Unlike magic modifiers, you cannot apply these for a specific portion of the pattern. Let's see some examples. Suppose I want to search for this. You can see these are the matches, and currently by default it does case sensitive search. So if I want to change it to insensitive search, then I can add backslash and lowercase c. So you can add this escape sequence anywhere in the pattern. So you can see matches this irrespective of case. By using uppercase C, you can force the search to be case sensitive. So for example, if I use the setting IC, then all the pattern matches will become case insensitive. So if I search for this, even without this escape sequence, you can see it matches case insensitively. In this scenario, if you want to enforce case sensitive search, then you can use uppercase C version, and now it will match only the exact case. So this applies for substitute command as well. So currently the searches happen case insensitively. So even lowercase cat matches all these terms. And now if I do substitute of cat with dog, all of these matches will be replaced. Instead, if I use uppercase C, then only the exact case will be replaced. Let me undo that and let me unset the IC option. And now if I use CAT as search term and dog as the replacement, and if I use the I flag, so this will change the search pattern to be matched case insensitively. So all of these three matches should be replaced. So you can see all three were replaced. Let me undo that. So even with the I flag active, if you use backslash uppercase C, then the search will become case sensitive again. So only this particular match should be replaced, and you can see only this was replaced. So to summarize, irrespective of flags and settings, you can control the sensitivity of the search pattern by using these escape sequences backslash lowercase c and backslash uppercase c. Let us learn how to change case of matched portions in the replacement section. Backslash and lowercase u will uppercase only the next character. backslash and uppercase U will uppercase all the following characters. Similarly, backslash and lowercase l will lowercase only the following character, and the uppercase version will lowercase all the following characters. By using backslash and lowercase e or uppercase e, you can stop case conversions. You can also use backslash and uppercase L or uppercase U to change further conversions. In other words, this will override the existing conversion. Let us see a few examples. Suppose I have an input with different number of words and I want to change only the starting character of these words to uppercase. So we need to match the start of the word. So we'll use the backslash and less than key for start of the word anchor. To match a lowercase alphabet character, we can use backslash and lowercase l. Note that this escape sequence will behave differently based on whether it is a search pattern or a replacement section. So once we have matched the starting character of each word, we can change the case in the replacement section. We need to change lowercase to uppercase. We can use backslash and either lowercase u or uppercase u because we are matching only a single character in the search pattern. And we can refer to that matched portion by using ampersand. Let's use a G flag to change all of these matches. So you get uppercase first character for all the starting characters of the words. Similarly, if you wanted to change the starting character of the words to lowercase, you can use start of the word anchor, use backslash and uppercase L to match a uppercase character, and in the replacement section, you can use backslash and lowercase l to change the matched character to lowercase. Here's one more example. Suppose I have words like these. So you have some alphabet characters, the underscore character, and then some more alphabet characters. We need to delete this underscore character and change this lowercase alphabet to uppercase. So let us use very magic mode and let us capture two lowercase alphabets separated by the underscore character. In the replacement section, this first match is kept as it is, and then the second match is changed to uppercase. And then we can use the G flag to change all such occurrences. Let's undo that. In fact, we can remove this capture group and instead we can use \zs to change the start of the match. So this will no longer be needed and we have only one capture group to take care. So we'll get the same result. Next, let us see how to change all the characters to lowercase. So dot star will match all the characters and we can use backslash uppercase L to change all the matched characters to lowercase. So you can see all have been changed to lowercase. Let me undo that. This was the original input. Next, suppose we have words separated by a colon character. We want to change all these words to have uppercase as the first word character and rest of the word characters as lowercase. So let us use \a to match alphabets either upper or lowercase, and can use the plus quantifier In the replacement section, there are two ways to handle this problem. We need to uppercase the first character and lowercase all the remaining characters. So this particular sequence can be written either \u and \uppercase L, or you can write it as \uppercase L followed by backslash and lowercase u. So Vim will take care irrespective of the order in which you specify this, and then our matched portion. So basically, the first character of the matched portion will be given to backslash and lowercase u. Rest of them will be given to backslash and uppercase L. So now the first character of the words are uppercase and rest of the characters are in lowercase. A final example, we have words separated by colon. We want the first word to be all lowercase and second word to be all uppercase. So let us capture the two words. We'll use the very magic mode and \a followed by the plus quantifier, and we have a colon character. We can put it inside the capture group itself. It will not be affected by case conversion, and another \a plus quantifier. So we have captured words separated by colon. We want first word as all lowercase. So \uppercase L and first capture group, and the second capture group should be all uppercase, right? So \uppercase U and \2. So you can see first word is all lowercase and second word is all uppercase. The / character is typically used as the delimiter for the substitute command. But you can use any other single byte character other than alphabets, digits, backslash, double quote, or the pipe character. This is useful if you want to include a / character in the search pattern or the replacement string. Let's see a simple example. Suppose you want to replace this portion with these two characters. If you use the / as the delimiter, then you will have to escape every / character in the search pattern as well as in the replacement string. So such occurrences of escaping / character is also known as leaning toothpick syndrome. So instead of this complication, you can simply use a different delimiter character so that you don't have to escape these /. So substitute, and instead of /, let's say we can use the comma character, and then our input to replace is the string, and then our replacement is tilde, which is a meta character, so you have to escape that, and then a / character. The I flag is to ignore case. So this string should get replaced as this output. Certain characters like tab, new line, carriage return, and so on have escape sequences to represent them. They can also be represented using their code point value in decimal, octal, and hexadecimal formats. Unlike character set escape sequences like \w, these escape sequences can be used inside character classes as well. Let us look at some examples. You can represent the tab character by using backslash and lowercase t. So let us search for a tab character, and there are two matches in this particular line. For the backspace character, you can use backslash and lowercase b. These two examples will behave the same in both search pattern and replacement string portions, whereas backslash r and backslash n behave differently. So if you want to match a carriage return in search pattern, you can use backslash and r. But if you use this in the replacement portion, you will get a new line character. For example, if I append backslash r to the end of the line, a new line character will be added. So you will see an empty line. Let's undo that. If you use backslash n in search pattern, you can match end of line characters. So these end of line characters will depend on the file format setting. It can be backslash n, backslash r, or backslash r followed by backslash n. So for example, if I use backslash n and press enter, you will see all the new line characters highlighted. Whereas earlier we saw that if you use backslash r, you will get new line in the replacement portion. And what happens if you use backslash n in the replacement string? You will get the ASCII null character. Next, let us see how we can specify characters by using their code points in the search pattern section. So you can represent them in decimal, octal, and hexadecimal formats. Suppose you want to search for the single quote character. So let us see how we can represent it in these three formats. First, let's see when the character is on the single quote character. And if we use the normal mode command GA, you will see these three values. So 39 is in the decimal format, 27 is in the hexadecimal format, and 47 is in the octal format. So let us try that. Backslash %d followed by 39. So you can see it matches the single quote character. Let us change it to octal. So we need 47. You can see it has matched the single quote character. And finally, let us use x27. So again it matches the single quote character. So when you use x, at maximum you can specify only 2 hexadecimal characters. The Unicode characters will need more than 2 digits. So in such cases, you can use lowercase u to specify a maximum of 4 hexadecimal characters and uppercase u to specify up to 8 hexadecimal characters. So these escape sequences to represent characters by using their code points is applicable only in the search pattern section. It has not been implemented in the replacement section, but in future versions this might become available. Let us see how to escape metacharacters. The easiest way to do it is to escape them using the backslash character. To match a backslash literally, you have to use double backslash. Depending on the pattern, you can also use a different magic modifier to reduce the need for escaping. Let us see some examples. The line anchors don't need escaping if they are not used in customary positions. So for example, if I search for B caret 2, so this will match this because this line anchor is not used as the anchor, it is at some other location. Similarly, if I use $4, so dollar is not at the end of the pattern. So this becomes an ordinary character, and you can see it matches in these locations. But suppose you want to match a string caret followed by super. Let's see what happens if we try to search for that. So caret and super. So there are no matches because you are using caret as a line anchor. So in such cases, you have to necessarily escape it using the backslash character. So now it matches these occurrences. Next, let us look at square brackets. When you are matching such characters, and if only one of them is present in the pattern, then you don't need to escape them. So for example, if I search for B, opening square bracket and 1, so this will happily match these occurrences. You don't need to escape this character. Similarly, if I am searching for 42 followed by closing square bracket, again this will match these characters literally. But suppose I want to search for B and within square brackets for 1, 2, 3. If I simply do B and 1, 2, 3 within the square brackets, then this becomes a character class. So this will match B followed by 1 or 2 or 3. But we want to match these characters literally. So if you escape one of them, then the character class will no longer be applicable. And you can see a match is found. So if you change this to escaping the opening square bracket, so that will also work. But the same thing cannot be used in substitute command. It will depend on the kind of pattern you are using. So for example, so if I am trying to search for B, opening square bracket and 1, and want to replace it with X, what will actually happen is this entire part will be matched literally as the search term. There is no replacement term, so this will be replaced with nothing. So you can see that simply disappeared. So let me undo that. So instead, you have to escape this opening square bracket. So now you can see it matches only these 3 characters. And when I press enter, this will be replaced with uppercase X. So here's an example where using a magic modifier can help instead of trying to escape all the meta characters. So suppose I want to match A star B dot C literally, I can use the very no magic modifier so that these characters will be treated literally. Next, let us look at a meta character in the replacement section. So if I want to replace and with ampersand, I need to necessarily escape it because ampersand is a meta character that gives the matched portion. So after escaping, you will get a literal ampersand character. So within character classes, we have meta characters like hyphen, caret, the closing square bracket, and so on. Easiest way to escape them is by using the backslash character. In addition, you can also place them in certain locations to match them literally. So for example, the hyphen character, if it is at the end or start of the character class, it will be treated literally. For the caret, it makes sense only if it is the first character within the character class. So if you place it anywhere else, then it will match this character literally instead of negating the character class. For the closing square bracket, you can place it as the first character of the character class. So this is a normal character class and this is a negated character class. In both cases, the closing square bracket is the first character. So this will be matched literally. When the replacement string starts with backslash equal to, it will be treated as a Vim expression. Let us see a few examples. Suppose you want to append the current date. So let us match a line containing date and colon, and let us set it to the start of the match. In replacement, we'll start with backslash equal to so that we can provide an expression. And then we can call a Vim function called strftime, and we can provide the date format we need. So year, month, and date. So result of this function will be appended to this string. So you can see the current date has been added. Next, let us see how to perform arithmetic operation on numbers that are matched. Suppose you want to multiply these numbers by 2. So we can match digit characters. In the replacement string, we'll use a function called submatch. So this is like backreferences. 0 gives the entire matched portion. If there are capture groups, then you can use corresponding numbers. So now we have the matched number, and we can multiply this by 2 and use the G flag as well. So these numbers should get multiplied by 2. You can see 4 becomes 8 and 10 becomes 20. A similar example, suppose our input is an arithmetic expression and we want to append the result of this expression. So let us capture the input arithmetic expression and let us set the start of the match. In the replacement, first we need to add space equal to space. This is just for readability purpose. So we are adding equal to. So this is just a normal string. And then we need to concatenate this with the result of this arithmetic expression. So we'll call the eval function and we'll pass the contents of this capture group. So we should get space equal to space and the result of this arithmetic expression. Next, let us see how to perform a substitution operation on a matched portion. So suppose this is our input line and we want to affect only the vowels that are within double quotes. So let us match our double quoted data. In the replacement, we'll call the substitute function. So for the substitute function, we need to provide what is the input we are working on. So we can use the submatch function again and we'll pass the entire captured portion. And our search pattern is vowel characters. In replacement, we just want to uppercase the matched characters and we want to change all the vowel characters. So we'll use the G flag. So essentially we are performing a substitute operation on the matched portion. So these vowel characters should get uppercased. And you can see this is not affected because this is not part of double quotes. For more details, you can go through the help topic substitute function because there are some subtle differences when compared to this substitute command. And finally, let's see an example with Perl. So let's go back to this earlier example where we want to multiply the numbers by 2. So if your Vim installation supports Perl, so then you can call the substitute operator from Perl. So we'll match the digits. Note that plus will not require a escape sequence because this is Perl based regular expression, not Vim. And in replacement, we'll use $& to represent the entire matched portion multiplied by 2. Since we have multiple numbers, we are using G flag, and the E flag allows us to use Perl code in replacement section. So these numbers should get multiplied by 2, and that's what we get. You will also note that I used dot as the range because unlike S, the default range is $1, that is the entire file contents. You can go through the help topic Perl do for more details. The functions which we saw like submatch, strftime, eval, etc. So you can find details about that in user_41.txt help topic. So that is the Vim script chapter. And for more details about \= you can go through the help topic sub-replace-expression. Let us look at some miscellaneous regular expression features. \% allows you to match inside a visually selected area only. For example, if you wanted to replace 10 with X only inside this visually selected area, then you can use \%V followed by search and replacement terms. So you can see this 10 is highlighted only within this visually selected area. Let me undo that, and instead with this visually selected area I apply the command without this modifier. You will see 10 will be replaced everywhere in the line. Next, let us look at \, percentage, and some set of characters within square brackets. For example, if I search for pa followed by \, percentage, and within square brackets the characters red in that particular order. So this will match spa because this character set can match 0 or more times. So this is a valid match, followed by one character which is R. So spa is also a valid match. The next character is E, but that can match only after the character R is also matched. So pair. And finally, it can match RED as well. So pa followed by RED. So this will match these characters as much as possible. In other words, longest match will win. So if you wanted to match these kind of patterns normally, then you will have to use something like this. So spa followed by the variations and then a quantifier to make it optional. So when you specify these alternatives, you have to be aware of the precedence factor as well. So that's why the longest term is specified first, and then the shortest term is pushed towards the end. So instead of all this, you can use this alternative, and you can nest these character sets. So for example, AP followed by \, percentage, and within a character set there's another character set and then some more characters. So what this means is AP can match by itself, and then it can match one of these two characters. So AP followed by P, that is apt, or AP followed by T, so that is apt. And after that, you can have these two characters in combination with either P or T. So you will have terms like APP followed by L or Y, or APT followed by L or Y. We have already seen how to use caret and dollar as line anchors. If you prefix these line anchors with backslash underscore, then you can match start of line and end of line anywhere in the pattern. So this is helpful when you have multi-line patterns. So let me give an example. Suppose I want to match uni followed by any character any number of times. And then I want to match a line that starts with M. So normally you might try with just caret and M. So this will not match because this is not used at the start of the pattern. So Vim does not know that this is meant as start of line anchor. Instead, it will match this caret character literally. So in such cases, we can use backslash underscore and then caret. So these three characters will mean start of line. So you can see uni has been matched followed by any character any number of times and then a character M only at the start of the line. So if this was not present, you can see it matches M till the last occurrence in the file. So similarly, when you are working with multi-line patterns, you can use backslash percentage followed by caret or dollar to match only at the start of the file and end of the file respectively. Next, let us look at a metacharacter tilde. So this represents the last replacement string. So for example, in this line, I am making a replacement apple with banana. So now, if you happen to use a search with tilde metacharacter, then that tilde will be replaced with banana because that was the last replacement string. So just by using tilde, you can indicate banana. You can also use other characters. So if you follow this by a backtick character, then you can see it matches only banana followed by backtick. So you can use this in replacement as well. For example, if I replace fig with tilde surrounded by parenthesis, then this will become banana surrounded by parenthesis. You can see fig is replaced with banana surrounded by parenthesis.